Welcome to the third episode of A Visual Approach to Optics, a Guide for Clinicians, narrated by Dr. John Gorfinkel. In the first two episodes, we covered 52 out of 175 slides. In the previous episode, we finished with the slide showing the eye as a multi-lens system. In previous diagrams, we drew only object points to show image points. Here we show an object point as one point on the surface of a whole object. The bottom point of this object gives off divergent rays, and these rays form an image point. There are an infinite number of points on the object, all of which give off diverging light. However, we have only shown the point at the bottom. Here we are showing the point at the top of the object giving off divergent light, which is then formed into an image point. Note that the image point is below the horizontal, whereas the object point is above it. Here we see the diagram of light coming off both the bottom point and top point of the object. These points have corresponding image points, as shown. We can infer that all the points in between the top and bottom have their corresponding image points, but we have not drawn the divergence ray diagrams for all the intervening points. Note that the whole object is upright, but the image is inverted, and this is typical of real images. It is assumed that the object is further away from the lens than its primary focal point, so that it forms a real image. Here we show the same divergence diagram, but have highlighted the central array in each group of diverging rays from the 2 points. These central rays cross through the lens undeviated and go through the optical center of the lens. These are called the chief rays. This diagram shows only the chief rays that were part of the set of rays diverging from each of the 2 points in the previous diagram. The chief rays here are used to form 2 similar triangles so that we can then use them to compute either distance or image size given other information. Warning: this type of diagram is not a divergence diagram. Objects give off divergent light. These rays appear to be converging, but they are not. These are rays coming from separate points. Every point gives off a set of diverging rays, but we have only shown one of these rays of each group. Let's call this type of diagram a chief ray diagram, which we use to calculate image versus object magnification. The previous diagram we can call a divergence diagram. Here is a numerical example. Let's look at the formulas. U over V equals O over I. Divergence V is 1 over distance V. Divergence U is 1 over distance U. Therefore, the magnification is equal to big U over big V equals small v over small u equals I over O. So if U is 4 meter and V is 5 meter, then the magnification is 5 over 4. Image size is 1.25 times the object size. Now that we know the magnification, we can calculate the size of the image or that of the object if we know the size of the other variable. Alternatively, we would need to know the angle shown here to calculate the image or object height. This is a divergence diagram showing different points on an object in the case of a diverging lens. Bottom point on the object here has a corresponding image point here, a virtual image. The top point on the object has a corresponding image point here. Here we can see the bottom point has its corresponding image point and the top point has its corresponding image point. All the in-between points can be inferred to have their corresponding image points. Note that the image in this virtual image is upright, unlike the case of the real image before, which was inverted. We can calculate magnification and image versus object height in a manner similar to the diagram with the converging lens. This is a diverging lens, and the object forms a triangle that is similar with the triangle formed by the image. This triangle is image height and image distance v. This triangle is object height and object distance u. They share the same common angle, therefore they are similar triangles. And using the same formulas, we can calculate as we did before. Up until now, we have generally been using algebra to calculate the relationship between object and image. We can also use geometry to analyze lens systems. What is the image distance and size if u is minus 0.5, that is, the object is 0.5 meter to the left of the lens. The power is 5 diopters of this lens, and the object height is 0.25 meter. First, we draw the lens, then we draw the secondary focal point, which is 0.2 meter to the right. We know that because the power is 5 diopters. We draw the object 0.5 meter to the left. We draw the parallel ray from the top object point. We know that any parallel ray that crosses the lens must have an image ray that goes through the secondary focal point. Since this is just part of the diagram that we've seen before, which defined secondary focal point, where we saw that non-vergent rays are then focused towards the secondary focal point. Although this is not a ray from infinity, this is one of the rays from a near object that is parallel to the horizontal, and therefore, like non-vergent rays that are horizontal, its corresponding image ray would go through the secondary focal point. Next, we draw a ray from the top of the object through the center of the lens, or the nodal point of the lens, and we extend it as far as needed until it crosses the first line. The junction is the corresponding image point. We can now draw the corresponding image of the object. Note that the image is inverted compared to the object. If we were careful in drawing this diagram according to the rules up till now, we would now be able to measure the distance to the image, distance v, and we would be able to measure the height I of the image. Using algebra to analyze the lens system, we would do it a little differently. U is minus 0.5, so big U is minus 2 diopters. U plus P equals V, so V is equal to minus 2 plus 5, which gives us 3. That means V distance is 0.33 meter. I over O equals V over U, So I is 0.33 over 0.5 times the object height of 0.25, which was given here. And therefore the image is 0.17 high and 0.33 away from the lens. It is generally easier to use algebra, but it is instructive to see that it can be done using geometry. What happens optically when an image is very far away at infinity? We cannot draw the same divergence diagram that we drew before of an image because the rays do not cross over each other in each group. We have the bottom point giving off divergent rays, and then the image rays are non-divergent. Similarly, the top point on the object gives off divergent rays, which have their corresponding image rays that are also non-divergent. The image is optically at infinity. However, the angle of the rays from the top point and is different than the rays from the bottom point. There is an angle theta between them, which we call the angular size of the image. Even though there is no divergence of the rays, we can still consider this to have an angular size. In this diagram, we see an object at infinity with top and bottom points. These give off parallel rays, a set from the top and a set from the bottom at an angle from each other as shown. These rays are then focused to form image points. This is a real image, which is inverted on the retina, as compared to the object that is very far away. Even though the rays are parallel in each set, we can see that the central ray of each set forms a visual angle. And this visual angle in the image space is the same as that in the object space, and ultimately results in an image on the retina which is inverted. If we know the visual angle here, and we know the distance from the nodal point to the image, we can calculate using trigonometry the actual height of the image on the retina. What is important here is the concept of visual angle. Both objects below have the same angular size on the retina. Which one looks bigger, the taller building farther away or the smaller tree closer to the observer? As can be seen by drawing only the central rays from the top and bottom of each object and carefully placing them in the diagram, we have similar triangles. The visual angle is the same for the tree and the tall building, and this visual angle will result in an image on the retina which depends on the distance from the nodal point. This distance from the nodal point doesn't change when looking at a tree versus at a tall building. In other words, both these objects result in the same size image on the retina, and they both have the same visual angle. This is where cortical brain function interprets object sizes based on their surroundings and on familiarity. This is an interpretation which is subject to error and can sometimes be utilized to create optical illusions. In this diagram, we see an object at the primary focal point of the lens. It has an image at infinity. The image rays are non-divergent. There are two important rays to be drawn from the top point of an object. One of the rays parallel to the horizontal must have a corresponding image ray that goes through the secondary focal point. We have seen a previous diagram in which non-vergent parallel rays must be focused at the secondary focal point. Even though this parallel ray starts from a near object and not infinity, it is still horizontal and parallel to the horizontal, so its image ray must go through the secondary focal point. The second important ray is the chief ray that connects the top of the object to the optical center of the lens. Note that these two rays, image rays, must be parallel to each other if they are to be non-vergent. In the case of the rays leaving the bottom point, the chief ray and parallel ray are one and the same. Here we see an example of an object that has a non-vergent image at infinity. We can calculate its angular size. We are given that the object has a height of 1/2 meter and a distance of 1/2 meter from the lens. The tangent of the angle is equal to the opposite over the adjacent. So tangent of the angle is 1, therefore the angle is 45 degrees. One way to magnify the angular size of an object to see it better is to move it closer. In this example, we have a 1/2 meter height object at √3/2 meters away, so that it has a 30-degree visual angle. Here we have moved it closer. Now it is 1/2 meter away from the observer, so that the visual angle is now 45 degrees. This works up to a point. The light coming off all points on the object is divergent, and if it is too close to the eye, the divergence will be too great for the eye to converge and form an image on the retina. One can accommodate to see more divergent light that comes from close objects up to a certain degree. So, although one can enlarge visual angle by moving it closer, it is limited by our ability to focus the object clearly. This is a reduced eye vergence diagram. What this means is that we have simplified the eye optics so that we consider the power to be in one plane, roughly around 60 diopters, in a single lens system. Here we have an object point far away at infinity. The rays are non-vergent. If the power of the lens is 60, then the rays will be focused to the secondary focal point of this lens system. The question is, what is that distance v? U plus p equal v, and u is 0, so p equals v. V is n prime over small v. N prime because the medium in the eye is more like that of water, with an n of 1.33. Small v equals n prime over large v, which equals 1.33 over 60, which is 0.022 meter or 22 millimeters. In other words, the distance between the front of the eye in this simplified diagram and the image on the retina is around 22 millimeters. This approximation works well enough for lenses that are added to the system in front of the eye. However, it cannot be used when calculating the lens inside the eye separate from the cornea. This is a model of the reduced eye as seen before, and the schematic eye, which is a better representation because it has two lenses representing the optical system of the eye as opposed to one lens. We must use the schematic eye representation when calculating for lens implants, and cannot simplify to a single lens The single lens simplification can only be used for lenses that are added in front, such as contact lenses or glasses. This is a schematic eye divergence diagram. It shows two lenses in the system, and we use this to calculate for lens implants in cataract surgery. As mentioned before, we would use U1 plus P1 equal V1 and U2 plus P2 equal V2 for each of the lens systems in a manner previously described. Here is a divergence diagram in the reduced eye using a one lens representation. We have an object with a bottom and a top point. Each has its set of rays forming image points. Note that divergence is shown occurring in this plane. However, the chief rays, one here and one here, are crossing at the nodal point in a slightly different plane. This is the plane of the nodal point, and it differs from the divergence plane. The reason that these two planes are separate and not in one plane as shown in earlier diagrams is because the index of refraction on this side is different than the index of refraction on the first side. This is the diagram typically drawn with the central or chief rays, as shown earlier, to form similar triangles to calculate magnifications and so on. Typically, the distance of an average eye from the cornea to the retina is 0.022 meter, whereas that from the nodal point is 0.017 meter. Here we superimpose a divergence diagram using the first plane and a nodal point diagram using the second plane. Typically there is a distance of about 5 millimeters between them. A better representation than even the schematic eye would be to have the two lenses, each with two principal planes. In practice, using one plane for each lens is sufficient in most cases. The thick lens approximation by two thin lenses has two nodal points and two principal planes to represent it. We have the chief ray going towards the first nodal point, and then we continue it from the second lens as if nothing happened in between on its way to the image. As mentioned before, we generally do not use the two thin lens approximation in clinical optics, because the one lens approximation is usually sufficient. Here we show the reduced eye with the question, what is the size of the blind spot at 1 meter from the eye given an optic nerve diameter of 1.5 millimeter? It has a visual angle of 5 degrees. So we draw the two similar triangles. Here is the size of the optic nerve, 1.5 millimeter, and this is 5 degrees angle between the two lines. We know that O over I equals U over V, so O equals IU over V, which is equal to 0.0015 meter times the distance 1, because we are given a distance of 1 meter away for the object, which will be the blind spot, divided by the distance V, which is given here at 0.017 meter. So the object height, in other words, the size of the blind spot, the diameter of the blind spot, will be 88.2 millimeter when it is 1 meter away. Note that the blind spot will have a visual angle of 5, but the actual size of it gets bigger the further away one goes from the eye. In other words, visual field defects have a cone-like spreading out pattern and not a tubular, tunnel-like shape as one goes away from the eye. Here we see an object at infinity with non-vergent light reaching the eye here. The convergence of the light is just right to form an image point on the retina. This eye is considered emmetropic, sees clearly at a distance. Any other state is called ametropia. Ametropia can be myopia or hyperopia. In the case of myopia, the non-vergent light is focused too close, too far in front of the retina. Back at the retina, the rays have diverged again and formed a blur circle. In this case, there's too much convergence for the length of this eye. Either the power of the system is too great, or the eye is too long for the optics of this system. In this case, the object that is far away is not converged sufficiently to form an image point on the retina. It actually intersects the retina and forms a blur circle. Either the optical system is insufficient to converge light for the length of this eye, or one can consider that the eye is too short for the optical system here.